Math 1332, Chapter 10, Probability and Counting Techniques, Section 3, Combinations, Video 5, one more example. I wanted to end this series for this section with an example comparing and contrasting combinations versus permutations, and that sometimes it's not always obvious which one it is. This one will also involve the fundamental counting principle. This is actually one problem with two parts. A. The 2017 baseball team at Ohio State University consisted of 10 freshmen, 7 sophomores, 12 juniors, and 5 seniors. The coaches want to choose 2 players from each class to represent the team at a booster club banquet. How many different ways can they choose? B. The coaches also need to choose 4 players overall to visit elementary schools in the community, with each player going to a different school. How many different ways can they make this choice? Well, let's start with the first one, shall we? In order to choose these players to represent the team at a booster club banquet, the coaches have 4 decisions to make. They have to choose the freshmen, they have to choose 2 freshmen, they have to choose 2 sophomores, they have to choose 2 juniors, and they have to choose 5 seniors. So from the fundamental counting principle perspective, they have 4 decisions to make. And then once they know how many ways to make each decision, we just multiply those answers together to get the total number of ways they can make all of these decisions. Let's start with the freshmen. There are 10 freshmen, and they want to choose 2. If they're going to send them to this booster club banquet, does it matter what order they choose them in? It does not. If they choose freshman Joe and freshman Bill, then it would be the same as if they chose freshman Bill and freshman Joe. So since the order they choose the 2 freshmen doesn't matter, it is a combination. And similarly, all of these will be combinations. Additionally, they're going to choose 2 from each class. So they're going to choose 2 freshmen, 2 sophomores, 2 juniors, and 2 seniors. They have 10 freshmen to choose from, 7 sophomores to choose from, 12 juniors to choose from, and 5 seniors to choose from. So this should give us the total number of ways they could pick the 8 players to go to the banquet. Let's clean up the dashes and work these out. All right, for the 10C2, that's going to be, remember that for a combination, the first number goes on top, the second number goes on bottom, as does the difference. For the next one, 7C2, the 7 goes on top, the 2 goes on the bottom, as does the difference. And all of these are factorial. For the 12C2, the 12 goes on top, the 10 goes on bottom, and the difference 2 goes on the bottom. I said that backwards. The 12 goes on the bottom. The second number 2 goes on the bottom, as does the difference. It really doesn't matter what order we do them in, but I always like writing the second number first on the bottom, followed by the difference. And then 5C2 will have 5 factorial on the bottom, 2 factorial on the 5 factorial on the top, 2 factorial on the bottom, and the difference 3 factorial on the bottom. Now we could expand and start canceling, but here's a nice little trick. When you're multiplying multiple fractions, any numerator, that factor that matches any denominator factor, can cancel. And 2 things jump out to me. This 10 factorial will totally wipe out that 10 factorial. And there's another. This 5 factorial will totally wipe out that one. That's good. That's less stuff we have to work with. Now let's see if there's any big chunks we can eliminate. I'm going to pick on the 12 factorial and the largest remaining factorial on the bottom, 8 factorial. When I spill out the 12 factorial, it will go 12, 11, 10, 9, and then everything 8 down will cancel with the 8 factorial. So I can cross out the 12 factorial and replace it with 12, 11, 10, 9, and that will wipe out the 8 factorial. Let's highlight what's left because let's not do that yet. Let's just start attacking things. The next largest factorial on the bottom is the 3 factorial, and the largest one remaining on the top is the 7 factorial. If we start spilling out the 7 factorial, 7, 6, 5, 4, we can stop at 3 because the rest will cancel with the 3 factorial. All right, now at this point, let's gather up everything that's left because it is getting kind of messy. And we'll make it all one giant fraction. In the first fraction, the only thing that's left is the 2 factorial, so we can spill that out as 2 times 1. In the second fraction, we have 7654 on top and 2 factorial. So let's spill out all those. We're in red here. 7654 and the 2 factorial from the second fraction. In the third fraction, we have the 12, 11, 10, 9 left, as well as the 2 factorial. So let's bring all that over. 12, 11, 10, 9, as well as the 2 factorial. And then in the last fraction, we have nothing left on the top and a 2 factorial on the bottom. So let's spread out the 2 factorial. All right, let's see if there's anything else we can get rid of. Notice the only numbers we have left on the bottom are a bunch of 2s, so we can find some things to cancel with them. That would be great. If I multiply these two 2s together, they become a 4, so all that cancels. This 2 can go into this 6 3 times, and this 2 can go into that 12 6 times. The only numbers left on the bottom are now 1s, so we're good there. And now we can just see what's left over. Let's get rid of all that right there. All right. So well, we don't need the fraction bar anymore. The only thing left on the bottom are 1s, and we do have quite a few things scattered around on the top, so let's track them down. This 7, this 3, that 5, that 6, that 11, that 10, and that 9. So we are left with 7 times 3 times 5. Things are running together here. 1 second. This is the problem with trying to do stuff in too little bit of a space. It is very easy for things to run together. I'm going to do my best to separate the work from the top with the work from the bottom. I would not do this unless you're proficient at it, but I'm pretty sure that's the correct partition. And now let's go back to writing what's left over. 7, 3, 5. Where'd my line go? There it is. I'm not sure what happened to that line. All right. 7, 3, 5, 6, 11, 10, and 9. And as braggadocios, it would be for me to try to multiply those in a row. Don't feel like doing that. Mentally, I should say. So we'll just get out a calculator and work it out. And I just mispressed a button. 7 times 3 times 5 times 6 times 11 times 10 times 9. And I get 623,700. Now, I do want to emphasize something. I know I did a lot of writing and canceling to get it down to a point where it was just a multiplication problem without fractions. But I know what some of you are probably thinking. Do I need to do all that? And the answer is not really. Here's what I mean. If you were to set up each of these individually, like we did before, they would look like this. Just using the formula for combinations. You could also choose to look at this as 4 smaller problems instead of 1 larger problem. For example, if you just looked at this problem by itself and worked it out on its own, you should get 45. And if you just worked out this problem on its own and did it by itself, you should get 21. If you work this problem by itself and worked it out, you should get 66. And if you worked this problem out by itself and figured it out, you should get 10. 99% sure those are right. Let me multiply those 4 numbers. 623,700 is what I got before. But I just wanted to show you that there's multiple ways to attack some of these larger problems, either by looking at the problem as a whole or looking at the pieces individually and then putting together as a whole. So it's up to you how you want to do these. And of course, if you have a calculator and know how to use it, you could type 10C2 times 7C2 times 12C2 times 5C2 equals and get the same answer. Let's take a look at part B and wrap up this video. The coach also needs to choose 4 players from 10 freshmen, 7 sophomores, 12 juniors, and 5 seniors overall to visit elementary schools in the community with each player going to a different school. How many different ways can they make this choice? Well, there's 2 key things to notice about this problem. Number 1 is the order they're selected matters because they're going to different schools. First player we pick goes to elementary school A, second player goes to elementary school B, third player to elementary school C, fourth player goes to elementary school D. So this will be a permutation. But the other thing about this problem that's kind of subtle but important is the distinction between classifications of students is irrelevant now. We're going to pick 4 players, and we don't care if you're freshman, sophomore, junior, or senior. So we're not looking at this as 10 freshmen, 7 sophomores, 12 juniors, and 5 seniors. We are now looking at this as 10 plus 7 plus 12 plus 5, which equals 34 players. Let me do that math again. 7 and 5 is 12, 12 is 24, plus 10 is 34 players. So they're not considering classifications anymore, but they're still going to pick 4 in a certain order out of 34. And because the order matters, this is a permutation. Of the 34 players, they're going to pick 4. And remember, in the permutation formula, the first number goes on top, but only the difference goes on bottom. 34 minus 4 is 30. And if we were to write out the factorials, the 34 factorial would start 34 times 33 times 32 times 31, but we wouldn't have to write the rest of it because the rest of it is 30 down to 1, which would cancel the 30 down to 1 from the 34 factorial in the bottom. So what does this equal? 1,113,024. So there's a lot of ways that they can pick 4 people to go to 4 certain schools in a particular order. And that's the end of this video, and that's the end of this section.